Right, welcome to today's stream. Sorry about this. I had a few problems with the streaming software, so I've had to fall back on my backup plan to stream. So this is not my usual software that I use to stream. This is just a backup that's got me working today and within a couple of minutes of the start of the stream. So here's our first question. Today we're going to be looking at some moments questions. There's some quite tricky ones. Here's a tricky one where you've got a pivot. Remember, the best way to deal with force, the normal reaction of the pivot, it's not pivot, sorry, it's resting on a rough horizontal ground. So we'll come on to pivot later. So it's resting on a rough horizontal ground, so remember what that involves. It's a 7-mark question. I'm going to give you 5 minutes to warm up with this one. One minute to go. Right. Right. So here we go. Let's get on with this question. And what we've got is uniform rod AB, mass 20 kilograms and length 4 meters. So we know this is 4 meters long, and we know that the mass has a force effect of 20G that's going to act 2 meters from here. And rests with one end on the rod on rough horizontal ground. So we're going to have some friction going this way, and we're going to have a normal reaction going this way. And we've got a force at B. I'm going to call that force B. Okay. And the line of action is force line in the vertical plane. And what that means is that all these forces are in the same vertical plane. So they all act in line with each other. It doesn't mean act vertically upwards. It just means as if you were to cut a line through this, you can imagine the screen being the plane. That's the plane, vertical plane it's talking about. Anyway, the coefficient of friction between the ground and the rod is 0.5. So we know that mu equals 0.5. And the magnitude of normal reaction, and we want to find the magnitude of the normal reaction of the ground at A. Okay, so we know that tan alpha, let's start with that piece of information, equals 3/4. So let's draw ourselves a right angle triangle. So if this is alpha, then 3/4, opposite over adjacent, then this must be 5. And sine alpha must equal 3/5. And cos alpha must equal 4/5. And that's what we're going to use in the rest of this question. We're going to also use the fact that F equals mu R, so that F will equal 0.5 R. Now, if we take moments about B, we can just negate B from the whole equation. And we know that we can write F in terms of R, and then the only unknown we've got is R. So let's work on that. So let's take moments about B, and we'll go clockwise. So therefore we're going to have R, and we're going to have a bit of R. So if this is alpha, then this angle here must be alpha. So the part of R we're going to be acting perpendicular. Remember, when doing moments, all the forces, when you're dealing with the moments, must be the perpendicular part of the force, which causes the turning effect. Okay, because we're imagining a pivot here, and actually what's going to be causing the turning effect is the perpendicular part of the force acting at that distance away. So the distance we've got here is 4 meters from here to here, and we're going to have R cos alpha as the perpendicular part. That. Then we're also going to have F. Now we're going to have this bit of F, so it's or this bit of F, depending on how you're looking at the diagram. And then we realize if that's alpha, then it's going to be the opposite part. So it's going to be F sine alpha. And also it's going to be 4 times that because it's distance away. So we've got F sine alpha as the moment of this force. And it's acting the opposite way. It's going to be wanting to take it that way around, whereas R wants to take it clockwise. And then we've got the G part of the force. So if that's alpha, this is 90 minus alpha. So this bit here must be alpha. So it's going to be the cos bit we're going to have. And that's also acting clockwise. So we're going to have minus, and its distance here is 2 meters. So we're going to have 2 times 20G times cos of alpha. And all those moments must equal 0 because we are in equilibrium. So let's put some things in. So we've got 4 times R times cos alpha. Now cos alpha is 4/5. So we've got 16/5 of R. Minus, now we know F equals 0.5 R. We know that sine alpha equals 3/5. So we've got 3/5 times a half. So that's going to give us 3/10 times 4. That should give us 12/10 times R, because we're replacing F with 0.5 R. So I did all of that bit of math ahead. Let me just check I got that right. 12. Yep, that looks good to me. So, and then we've got minus 40G cos alpha. Now, cos alpha is 4/5. So we're going to have 160 over 5 G equals 0. So let's just let me just zoom out to give myself a bit more space. Okay. Bring that back up again. So we have got 16 fifths minus 6/5 of r. And on the other side, we take this to the other side, this gives us 32g. So therefore 2r will equal 32g. So r will equal 16g newtons. Let's see if there's any questions in the chat. Doesn't seem to be any at the moment. Do feel free to post them. I can always come back to them after the next question. So moving on to the next question. Here we go, question 10. This one's a little bit trickier and a bit longer. Let's give you 7 minutes to have a go at this one and get stuck into it. Off you go. Right, so here we go. Sorry about this, I left it a bit zoomed for you. Let's look at this, and we're going to put here, we've got normal reaction on A going up the rope. What we've got, one rope is attached to A, the other rope attached to the point C. AC equals D meters shown in the figure. The beam is modeled as a uniform rod, so the weight will be acting downwards at 2 meters, and it's W. The tension rope attached at C is double the tension rope attached at A. So if we got R going up here, we've got 2R going up here. And we want to find the value of D. Now, my instant thought was to resolve this way. And you get 3R equals W. It's a nice, easy equation. But actually, it doesn't really help us any. But it's always quite nice to just quickly put out some easy equations and get going on the question. But then if we take moments about W, then the unknowns become R and they become D. And you'll see that the R's will cancel, therefore. If we take the moments about W, we've got this point, which is 2 meters away. We've got going clockwise, that's going to be going clockwise, so that one will be 2R. And then we've got this one, effectively, is going to be going anti-clockwise. This one's going that way, this one's going to be going that way if we've got our pivot point here. Okay. I'm going to undo those drawings just to not get too cluttered in our diagram. So therefore we've got 2R minus 2R, and the distance it's away is going to be 2 meters away from D. So we've got D minus 2 meters our distance from there, and that gives us 0. And what you'll notice is the R's just cancel. Oops, cancel the wrong thing there. Try again. So the R's just cancel, and we are just left with 2 is equal to 2D minus 4. And therefore, bring the 4 to this side, it gives us 6. And we've got 2D equals 6, so therefore D will equal 3 meters. Now, for this part, we've got a small load of weight kW newtons is attached to the beam at B. So we've got kW going on here. The beam remains in equilibrium in the horizontal position. The load is modeled particle. The tension in the rope attached to C is now 4 times. Let's just undo that. Put 4 times here. Okay, the tension at A. Now, if we do a quick resolving vertically, what we can see is we've got 5R okay, will equal what we've got here. We've got W and we've got a KW. So we're going to have a 1 plus K lot of W going on there. And if we take moments about, let's go for A now. We take moments about A. So if we go about A clockwise, so I'm just going to use some shorthand, clockwise about A here, we're going to get, let's have a look, we're going to have 2W here, going clockwise. And then we're going to have minus 3 times 4R. And then we're going to have 4 times kW going the other way. And they must add up to give us 0. Now we know that 5R must equal 1 plus kW, so therefore R will equal all that over 5. So I'm going to replace this R with that. So I'm going to get 2W minus, that's 12, over 5 times 1 plus kW. So what I've done is I've divided all of that by 5, or you could just think of dividing this by 5 and putting it into here to get 12/5. And then we got the 1 plus kW plus another 4 kW equals 0. And what you will notice here is that all the W's cancel. And therefore we've got an equation with just K in it. So we've got 2 minus 12/5 minus 12/5 K plus 4 K equals 0. And let's just simplify that down. Well, actually, let's save some time. We're just going to get to the answer. Solve that, and you get K equals a quarter. All right. If you simplify that all down, and this comes out to be minus 2/5. This comes out to be 8/5, and therefore you just get 2 divided by 8, which is a quarter. Right. Our next question. Here, question 11. Let's just zoom in so you can see a bit more of this. I think it's this one held by a rope. Attached to point B is showing the beam is uniform and it's hinged. So this is the hinge question. So do remember, when you hinge questions, the best thing to do is to try and think of the hinge as being the normal reaction of the hinge being two perpendicular forces. So give yourself one going horizontally and one going vertically. That will make the question a lot easier dealing with the hinge. So let's give you 5 minutes to have a go at that, especially as I've given you a big hint of how to do it. Off you go. One minute to go. Right, so that's 5 minutes. See how you got on with that. So we know we've got 63 newtons acting up that way. And we've got uniform beam, so it's going to be at the midpoint of here. It has 2 kilograms, so it's got 2G acting down that way. Do we know the length of the rod? I don't think we do. So we're going to call that this D there. Okay, what I'm also going to do is model the reaction forces here, okay, on this point as going to be X that way and going to be Y that way. Now, we want to find the length of AB. So, obviously, the length of AB is going to be 2 times D. So, let's take some moments about A. Let me just zoom out a bit to give myself some more space. So, let's take moments about A. And we'll go clockwise. The reason I'm going to take moments about A basically gets rid of all the unknowns there. And so therefore I'm dealing with things. I know the 2G and I know this force here. So if I take moments about here, then I have got the 2G times by D is acting clockwise. Let's put that down. So we've got 2G times D. And I'm going to take away from that the amount of the 63 that acts anti-clockwise, and we want the perpendicular bit of that. So the perpendicular bit of that is going to be sine 30 lots. Okay, so we know that this distance is 0.14. So we're going to take away 63 sine 30 times by 0.14. And they're going to be equal to 0. There's no other forces acting. The only forces acting on this rod are the rope going up here and the weight down, and then there's the hinge here. But by taking moments about A, because the distance is 0, they all disappear. So what do we have? We have that D will equal 63 times by 0.14. Now, sine of 30 is just equal to a half. So therefore, we can just put that on the bottom and then times it by the 2G. So that gives us 4G on the bottom. So we get D is equal to 0.225 meters. Right, moving on. We want to find the magnitude of the resultant of the reaction of the hinge on the beam at A. So if we resolve horizontally, then we're going to have the X will just equal the horizontal component of the 63 because the weight and the Y just act vertically. So we take the horizontal component of that, so it's just going to be 63 on 30. And then if we resolve vertically, then what we're going to have is we're going to have Y plus the 63 component here, okay, will equal the 2G component here. So we've got Y plus, what's that, 63 sine B 30 is going to equal what's acting downwards, 2G. And just thinking about that. Okay, so therefore we can find the magnitude. So we can therefore replace that Y is equal to 2G minus 63 sine 30. And then all we've got to do to find the magnitude, okay, of the resultant reaction. Okay, is going to be equal to the square root of x squared plus y squared. Okay, so you've got your x component going that way and your y component going that way, and therefore the reaction is going to be somewhere between them, and it's going to have that magnitude. So you just type all of that into your calculator, type all this into calculator, square each of them, add them together, square root, and you get 56 newtons as your answer. Right, how are we doing for time? I think we've got just enough time to get the last question in. So here's our last question, question 12. It's a 10 marker. I'll give you 5 minutes to have a go at that, and then that will finish off our stream for today. So 5 minutes, see how far you can get with this question. 1 minute to go. Right, here we go. So let's get into this question here. Just make sure I've got my answers up. Oh, we have actually got another question, but we'll stop after this one. So we've got our ladder of AB, mass M and length 4A, and has one end A resting on a rough horizontal ground. So we have friction acting that way probably, before I even read the rest of the question, and probably a normal reaction going on that way. We got mass M. So mass M, and we don't know if it's uniform yet, so let's carry on. But the other end of B rests against a smooth horizontal vertical wall. So all we got is a normal reaction here, which I call R1. We don't have any of the forces acting at that point because it's smooth. A load of mass 3m is fixed out of the point C. So there's 3m, G acting down there, where AC equals A. So this distance here is A. The ladder's model's uniform rod, so we do know it's uniform. So we've got 2A getting ourselves to here. So we have, what was it, mg acting at that there. So perpendicular to the wall, the load is modeled as a particle. The ladder rests in limiting equilibrium, making an angle of 30 degrees with the wall, as shown in figure 2. So limiting equilibrium means we've got F equals mu r going on in this question. So, find the coefficient of friction between the ladder and the ground. Well, let's start off by resolving vertically. It's always a useful thing to do. And we'll see that R will equal 4mg. Okay, the reason why I've done that is because obviously it gets this unknown into a series of knowns. And we know that F equals mu R. So actually what we know is find the coefficient. So we know that F equals mu times 4mg as well in this question. Now, if we take moments about B and go clockwise. Now, we take moments about B because then we can get rid of this other unknown R1 here, and we're dealing with mg's and stuff. So let's start off with this one. So we've got 2a times mg. That's going to be acting. So if this angle is 30, then it's going to be sine of 30, the perpendicular component. Remember, we want to work out that perpendicular bit. That bit there is 30. Okay, if you can see into there. And we want to work out the perpendicular bit. That's going to be mg sine 30, then times by the distance away from B. Then we're going to add on to that. Actually, is that going to be clockwise? That's going to be anti-clockwise. So I need to change my direction because these are anti-clockwise forces. So let's just change that to that way. So next, I'm going to do the 3amg. This one here, and that because it's 3a times. I need another 3 in there, don't I? Another 3a times 3mg. And then we've got sine of 30 going on there. I'm just going to zoom out a bit, give myself some more space. And then I'm going to be having 4a times f cos 30, because that angle there is going to be 30. So I'm going to have 4a times f cos 30. Okay, and I'm also going to have 4a times the r, and it's going to be the sine 30 part of that. So I'm going to have minus 4a times r sine of 30. And all of those are going to add up to equal 0. So going through, what we can see is we have an A, an A, an A, an A. Let's get rid of the A's. Let's just cancel those out. There we go, all the A's. And we can start simplifying. So sine of 30 is a half. So that's just going to leave me mg here. Plus sine of 30 is a half. So I'm going to have 9 mg over 2. And then I'm going to have, now the F is equal to 4 mg times mu. So I'm going to have 16 mg times cos of 30 root 3 over 2. So I'm going to have minus 16 mu mg times root 3 over 2. So we've got the mg, mu times 4 mg times by the 4. That gives me the 4f bit, and then times cos 30, which is this bit. And then we've got r equals 4 mg, so I'm going to have a 16 mg times a half, so that's going to give me 8 mg equals 0. And what you realise is we can also cancel out m and g. Just leaves me 1 here. Okay, and when I simplify all of this down, I'm going to get 16 root 3 over 2 times mu minus 2.5 equals 0. And in my answer, I've got mu equals 5 over 16 root 3. I've not simplified that down. You can type that into your calculator and see if that matches up with your answer. So I think we've been going for 45 minutes now. I think that's more than enough time. So this question, if you go to this, if you get this notebook, you can find I've put the answer in here. In fact, what I'll do is I'll put it on screen for you. There's my answer to question 13. So you can see there's my answer on question 13. You can have a go at this later, take a screenshot of that on the video and just see how that compares to your answer. So I won't put that into another stream because one question in the stream is not really worth doing. And the next one on the mechanics side of things, as you can see, popping its head up here, is going to be inclined planes and all sorts of other things. So there you go. Next one is going to be a pure maths one, and it's going to be in 2 days' time. Thank you.